Let me start by identifying that my presentations of physics follow a model I call Sala physics. It is a rethinking of physics explanations as given in the conventionally taught school science curriculum when what is being taught is not right. I apologize for the delay in getting this to you, but it takes time and effort to research these things. This video is presented more or less as a truncated Sala physics video lesson with asides. In looking at some of the definitions and examples for fair use online, I feel pretty confident that the Sala physics materials I'll be generating fall easily within those guidelines. These rules seem to sum up the guidelines for fair use of copyrighted material pretty well. Even though I was asking only about the future online availability of the links posted by CalTech for the Feynman lectures, and got your assurance that as long as there is a CalTech, they will persist, you expanded that to suggest giving me some level of permission based on my projected use of the material, and thus this video. I assume that in addition to the Feynman lectures textbook, there are other books in the various science departments that are also available online. There is no shortage of Feynman videos online that I would have the same concerns about their future availability if the posters did not have the right to post the videos. If specific permissions are granted for use of the Feynman lectures, it would be good if they would also extend to other textbooks and videos that may be controlled by CalTech. The referenced videos are not CalTech videos. In this example, I include clips from the video and then continue with my own analysis, while providing a link to the video as a whole so my students could go and see the overall context for the video as they are so inclined. The first clip is from an Encyclopedia Britannica film from 1950 on the subject of sound. Sound is generated by a moving object. In the video, a tuning fork is used. Then the fork is animated to show how it generates sound waves.
In this film, we shall study how sounds are produced and the principal auditory differences of sounds. To begin with, what is involved in producing sounds? To help answer this question, we experiment first with a tuning fork. When the fork is struck, its prongs begin to vibrate. These vibrations set up invisible waves in the surrounding air. We can picture these waves as animated drawings. Striking the prongs distorts them. Like other solid objects, these prongs resist distortion. They spring back and forth, thus producing new distortions. Each movement or vibration sets up new disturbances, or sound wave impulses. These continue as long as the prongs are in motion. The speed with which sound waves move depends upon the medium through which they pass. We will assume that these waves are being transmitted by air molecules. Every time the prongs move apart, they push against the adjacent air. In turn, this movement affects the air further on. In this segment of the wave, we can see that some molecules are pushed relatively close together. These represent condensations of air. Each time the prongs spring inward, a partial vacuum forms in their vicinity. Air molecules nearby move into this vacuum, leaving a rarefied zone behind. Thus, there are alternate zones of condensation and rarefaction of the air.
That is the way sound was taught in school science classes in 1950, and the explanation remains unchanged. As students get into higher grades, the explanation becomes more language specific. For example, the condensations and rarefactions described in the film are presented as more conceptual longitudinal compression waves. But there are many problems with sound as it is described in the film. And those problems are clearly seen throughout the science and engineering communities and extend even to Feynman's chapter on the subject. The title of this YouTube video is Sound Intensity and Decibels Distinctly Defined Dude, and is presented by a fellow with a PhD in physics who is a high school physics teacher. In the video, sound is described as energy that's emitted by the sound source.
In order to understand the idea of intensity, we need to define it. Intensity is defined as the energy going through some area divided by that area divided by time also. So we define some area here, and we say that there must be energy flowing through this area. Let's see, this is an area A, and there's energy going through it.
By claiming that the sound is emitted from the source as energy, Doc Physics has already painted himself into a corner. Since he's imposed an energy budget on himself, he's now not allowed to have more total energy available than the sound source produces.
Intensity is cool, and so I want you to consider somebody, I don't know, let's say this, this is a siren going off right here, and sound is going out from that siren, right? And I guess I'm drawing wave peaks going out from that siren. We're going to be doing this a lot as we move on here. And the issue is, you know that it gets quieter as you get further away. Right? You know that it's going to get quieter as we get further away. And the reason it gets quieter is because the wee-oo, wee-oo of the siren is getting spread out. So why don't I ask you, if we're saying the power of the siren is fixed, it's going to keep making that wee-oo, wee-oo sound. If I'm over here, then there's some area that, oh man, this has got to be three-dimensional. This is going to be kind of tricky. There's some area that energy is spread over here. How does that area depend on how far we are away from the source? How does that area depend on aura? And to do that, we need to consider, if we snap our fingers, if we have a siren or something, what's happening to that sound wave? Where does it go? You know that on a lake, if I drop a stone in a lake, then it will make these kind of ripples that go out in a circle. But is that where the sound goes? Does the sound go out in a circle? No way. Sound goes out in a sphere. So we're talking about the area. In order to find the area here, we need the area of the sphere of radius r, the distance that we are away. So if we say, let's introduce this a little bit. This would be intensity of a sound in sound from a point source at distance r. Here's our intensity. In that case, I is going to be, well, the power of the point source, and then we need to divide it by the surface area of the sphere that's at that distance r, because as the sound spreads out, it gets weaker. We're taking that energy and spreading it over a greater and greater area, so the intensity at each square meter here is less than the intensity of a similar square meter here. Consider this. Here's this square meter here, right? What if I came up here, much closer, and I studied this square meter? Would you agree that I'm getting a much greater fraction of the total energy of the source at this distance with my square meter than I would be at this distance with my square meter?
Doc Physics tells us that as the sound spreads out, that energy gets spread out over a larger and larger area, and thus gets weaker as the sound travels farther. Solid physics does not believe that to be true. But for now, let's continue.
So if you do this calculation, this is an interesting calculation about the smallest intensity that human ears can hear. This turns out that it's a vibration. You know, sound is a vibration of air particles, right? So the air particles right in front of your eardrum are vibrating less than a width of one molecule at this intensity. You can hear it in a perfectly silent room. You can hear the vibration of the air molecules even if they move less than one molecule.
Doc physics arrives at a conclusion that humans can hear sounds that move air molecules by less than the width of one molecule. He also makes the statement that,
you know, sound is a vibration of air particles, right?
Certainly, all classically trained scientists and physicists seem to believe that, but solid physics does not believe that individual air molecules are vibrating. However, in the solid physics model, the molecules are generally displaced by a much tinier amount than even the movement Doc physics describes. Doc physics goes on to make the case for sound falling off according to the inverse square law, and does it as a strictly mathematical exercise.
But I want you to notice that there's a range not just of like 1 to 5, but a range of 10 to the negative 12th to 10 to the 3rd. That's a factor. Oh man. That's a factor of, well, let's see this. We can write these out. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. That's an enormous range of human hearing. In fact, this is a million, this is a billion, that's a trillion. That's a quadrillion. You can hear sounds that are 1 quadrillion times different from other sounds. So we don't like this. This is too big of a range to handle actually writing the numbers. So we introduced this fun system called decibels. And a decibel is a way for us to keep track of a really big range of sounds. So a decibel is related to the idea of loudness. That's an E. A decibel is related to the idea of loudness, not intensity, but intensity level. I'll put another arrow over here and say that a decibel measures intensity level, and I better put that in quotes so that you can dig this. Intensity level. It's not strictly speaking intensity because we're going to do a little bit of division. So intensity is going to be defined like this. I want to, not intensity, but intensity level, the decibel. It will be defined like this. I've got intensity, and I want to compare that intensity to I naught, the faintest intensity that you can possibly hear. So this is going to be a dimensionless number, and as we saw before, this number will be anywhere between 1, if intensity is I naught, up to, I guess, a quadrillion. So it's between 1 and 10 to the 15th or something. That's a huge range. So let's instead not just take this ratio, but take the log of it. And for some stupid historical reasons, we use the number 10 here. We ought to use the number E. Can you figure out why we use the number 10? I hate that. Now, instead, we're going to, well, okay, so we use log base 10, which is frustrating, but then there's another historical complication that says we're not just going to do this, which would be very sensible on its own. Then we get a range of bells between 1 and 15, but because it's a decibel, we're actually going to multiply this by 10. Oh my gosh. So it looks rather complicated, but we'll spend some time working with it in class. The point is that I naught is the faintest sound that you can hear, and it's 10 to the negative 12th watts per square meter. And now you can do calculations with decibels.
He says that because of the enormous range of sound intensities we are able to hear, there is a need to express that fall-off rate using a logarithmic scale, which is based on the decibel. Sound does not fall off as the inverse square law of distance. It can be clearly demonstrated to not fall off at that rate. Here is a recording of a train horn from a distance of about 1.25 miles. The sound intensity, as heard and recorded, is much greater than predicted by the mathematically derived fall-off rate. But apparently no conventionally trained physicist in the history of the Earth has ever made that measurement, because they are absolutely convinced that the fall-off rate of the sound is as their math dictates. It is true that the sound does get weaker as the distance increases, but for reasons that are completely misunderstood by the science and engineering communities. And we lose the ability to hear the sound long before the intensity drops to the trillionth of a watt claimed by Doc Physics. To resolve these issues, we need to come up with a different explanation for how sound is produced and coupled to the air and other media, and is propagated, and is detected. That corrected explanation is the original material presented by Soliphysics on the topic, and on which I would hold the copyright. Now I'll give a specific, explicit example of how I would use and reference the Feynman textbook. Chapter 47 of that book is important since it addresses not just sound, but the nature of waves and their applicability to physics, and also gives information about light and electromagnetic waves. References to the mediums of propagation for both light and sound are given. Within the soliphysics model, the chapter is also useful for providing a basis and a launching point for the soliphysics theory of gravity and the geometric aspects of propagated phenomena. But for this video, I'll restrict myself to a similar constraint of just sound as with the Doc Physics video. Doc Physics concentrated on sound intensity. Mr. Feynman mostly makes the case for the speed that sound travels through the air. I'll start with directly quoted material from the book. We shall take the simplest example here, the propagation of sound in one dimension. To carry out such a derivation, it is necessary first to have some kind of understanding of what is going on. Fundamentally, what is involved is that if an object is moved at one place in the air, we observe that there is a disturbance which travels through the air. If we ask what kind of disturbance, we would say that we would expect that the motion of the object produces a change of pressure. Of course, if the object is moved gently, the air merely flows around it. But what we are concerned with is a rapid motion so that there is not sufficient time for such a flow. Then, with the motion, the air is compressed, and a change of pressure is produced, which pushes on additional air. This air is, in turn, compressed, which leads again to an extra pressure, and a wave is propagated. The Encyclopedia Britannica film showed sound working just the way Mr. Feynman describes. A lot of videos have been produced which duplicate this explanation. Here's a more recent one.
When an object vibrates, it pushes the surrounding air molecules into one another, starting a chain reaction of collisions through the air. These collisions travel in waves. When they strike your eardrum, it vibrates. This vibration is converted into electrical signals that your brain recognizes as sound.
But regardless of how artfully a quote or explanation may be read or stated, or how elegantly the graphic is presented, it's still wrong if it's conceptually incorrect. I really do need to use actual material and quotes from trusted sources in my presentations. If I paraphrase the conventionally taught version, even accurately, there is a strong bias against salophysics having gotten it right. That bias against salophysics can at least be mitigated, maybe a little, hopefully, by actually presenting the material in its original form from the accepted, respected scientists and physicists saying it in their own exact words, but still not based on their mathematical efforts, since we've already seen in the doc physics example, and with proper analysis will see in the Feynman example, the mathematical derivations of conventionally taught physicists are so often wrong because the math is based on incorrect concept. Feynman goes on to begin to develop the basis for his mathematically derived answer regarding the propagation of sound. We now want to formulate such a process. We have to decide what variables we need. In our particular problem, we would need to know how much the air has moved so that the air displacement in the sound wave is certainly one relevant variable. In addition, we would like to describe how air density changes and is displaced. The air pressure also changes, so this is another variable of interest. Then, of course, the air has velocity, so we shall have to describe the velocity of the air molecules. The air particles also have accelerations, but as we list these many variables, we soon realize that the velocity and acceleration would be known if we knew how the air displacement varies with time. Most certainly, Mr. Feynman is well aware of the speed of sound based on actual measurements of the time it takes sound to travel a specific distance. As Feynman stated, he is also aware of the speed of air molecules and knows that the results of his mathematical derivations need to satisfy these parameters. Nobody has actually directly measured the speed of a molecule, so the speed is mathematically derived from the behavior of macro phenomena.
Now let's ask a very basic question. You are sitting, I assume, in a room filled with air, unless you're doing this on a space shuttle or something like that. And how fast are those air molecules around you going at? Well, the motion of an air molecule can be in the x, y, and z directions. Each of those has an energy of about half kT, so the total motion energy is going to be about 3/2 kT. There's also going to be vibration and rotation, but it's the motion we're interested in here. Now that's going to be equal to the kinetic energy half mv squared of the motion of a typical particle. Some are moving left, some are moving right, up, down, whatever, but on average this is going to be equal to that. So if we set 3/2 kt equals half mv squared, rearrange, we find that the velocity is going to be roughly root 3kt over m. Now, what's the mass of an air molecule? I mean, air is mostly nitrogen, and nitrogen is diatomic at normal atmospheric conditions. So a typical molecule has 2 nitrogen atoms. Nitrogen has an atomic mass of 14, so it's got 14 nucleons, protons plus neutrons in each atom. So the mass of a molecule is going to be about the atomic mass unit times 14 times 2, because it's a diatomic molecule, which comes out as about 4.6 by 10 to the minus 26 kilograms. Now if we plug this in for room temperature, 300 Kelvin, we find the typical velocity of air is about 500 meters per second.
Because of the way sound actually works, it can be shown that mathematically derived molecular speed is not correct. Sound is not about density changes and compressions of air molecules, and saying that it is just conceptually wrong. Mr. Feynman accepts things that are taught in the conventional school science curriculum that just are not true. And like Doc Physics, by an abiding belief in the infallibility of mathematical derivation. We can see this very strongly in this Feynman quote. The point here, in a certain sense, is the derivation itself. This problem of explaining new phenomena in terms of old ones, when we know the laws of the old ones, is perhaps the greatest art of mathematical physics. The mathematical physicist has 2 problems. One is to find solutions given the equations, and the other is to find the equations which describe a new phenomenon. The derivation here is an example of the second kind of problem. Does Feynman get it wrong because he figured it out mathematically? Not at all. The question Salophysics asks is if he did the math based on correct concepts of how sound actually works. It's imperative, even when doing the most rigorous mathematical derivations, to have gotten the core concept of what you're trying to mathematically derive right. If you have the wrong concept, all the math in the universe will not take you to the correct answer. To get the concept of sound right, we cannot think in terms of an air mass and the density or pressure of an air mass. We cannot even think in terms of the relative proximity of even 2 air molecules. We need to consider only the interaction of each and every air molecule with the moving object, and how each molecule is shifted in time and space by that movement, and how that change of position of each molecule can persist for appreciable amounts of time and over an appreciable distance as it propagates, and then how it's detected. Sound is not and does not propagate as sound waves or any other type of waves, and the Salophysics explanation departs from the Feynman version at this point. At the end of the Salophysics explanation, a comparison between the accuracy and viability of the standard science curriculum version and the Salophysics version will be given, and may include further quotes from the Feynman text and other sources. When I worked as a tech writer and technical instructor, I don't recall actually signing anything that would give the company the rights to what I wrote and the materials never showed my name as the author. That was just tacitly expected. As you had mentioned about Feynman's work, since he was employed by CalTech, are there any special precautions I need to take when using other people to assist in the production of my materials? Are there any standard forms for this? I have been leaving footprints around the internet of some of the solid physics concepts and explanations of physics with the hope that if my copyrights are challenged, that I have something that shows it was published somewhere with a good, solid timestamp. At least I hope it can work that way. Anyway, I thank you for your time and patience, and hope I can get some good guidance on how I can most safely and effectively use other people's materials in my own solid physics presentations.